The next topic that we are going to study in operational amplifiers is slew rate. The definition of slew rate is a maximum rate at which the amplifier output can change in volts per microsecond, or it is a measure of how fast the op-amp is able to respond to the change in inputs. The unit of slew rate is given as volt per microsecond, or slew rate is equal to delta V naught divided by delta Vt. Now what is delta V naught? Delta V naught is a change in input, and delta T is the change in time. So if you see here, we say that slew rate is equal to delta V naught divided by delta T, and normally the value of delta T should be very small. That means that the slew rate output should, for an operational amplifier, the output should change as soon as the input changes, or the time period required to change should be very, very small. So this should be very small. Very small. So in that case, your slew rate should be a very high value. If you remember, when we had studied the characteristics of an ideal operational amplifier, we studied that the ideal operational amplifier will have a slew rate of infinity, or it's a very high value. Now always remember, the unit of time is always in microseconds. Now, what is the importance of slew rate in case of an operational amplifier? It is a parameter which will specify the maximum rate of change of the output voltage. That means when you are giving a step input, especially, it will tell you how fast your output can change. And if you do not choose an operational amplifier with proper slew rate, the output will not be what you require, or the output will not be the duplicate or the replica of the input signal that you have applied. I'll explain to this with the help of a circuit diagram. Let us see what is the effect of slew rate on a voltage follower. I hope all of you remember what is a voltage follower or a unity gain amplifier. A voltage follower is a amplifier circuit where the gain is equal to 1. Let us see the circuit diagram. This is a non-inverting amplifier where the input is given to the positive terminal. So this is the input. Then the inverting terminal is connected as the feedback path, but in the feedback path there is no feedback resistance. The RF value is equal to 0. So this we have already studied. Now I'm going to apply an input, a step input or a square wave input to the voltage follower. So if you see here, the amplitude of the square wave that I've applied is 5 volt. So what do you expect in this case? You expect that the output will be like this, because for a voltage follower there is no gain. So whatever input you give, the same should come as your output. But that is not the case in terms of a practical voltage follower if the slew rate is not proper. So practically this is how your waveform will look like. If you see that black wave, the black line, so that means your wave will actually have it will take a time for the wave to reach the maximum value. So that is given by the T. So if you see here, the output will be like this. Then it will take a time to reach 5 volt. Then it will stay at 5 volt. Then it will take a time to come back to 0. So this output that you get is slightly different from the output that you expect. And there is a T, time delay for the output to reach from 0 to 5 or from 5 to 0. So even this time is T. So this distortion in the wave is because of the result of slew rate. I will show you one more example which will become clear for you. Let us assume that we are applying an input to an operational amplifier which has a slew rate of 0.5 volt per microsecond. So this is the input that I'm going to apply. So I'm applying an input which is a square wave or a step input which has an amplitude of 5 volt. And the time period or the on time of the step signal or the square wave is 20 microsecond. And it says that it has a slew rate of 0.5 volt per microsecond. So you have here your slew rate is 0.5 volt per microseconds. So that means in 1 microsecond your output will change only 0.5 volt. So that means here I have to change my output from 0 to 5 volt. So that means how much time do I require? I require at least 10 microsecond for my output to change from 0 to 5 volt. Or the opposite, if my output I want to change from 5 to 0, still I would require 10 microseconds. So let me see how the output would be. You see here, as I told, the output will take 10 microseconds to reach to 5 volt. So if you see here, see this black line in the output. The black line in the output is the time that is required for the output to take up to 0 to 5 volt. So this time would be approximately 10 microseconds. Even this would be 10 microseconds. You understand? So for the signal to reach from 0 volt to 5 volt, because of the slew rate problem, it will take at least 10 microsecond. Similarly, from 5 volt to 0 volt, because of the slew rate, it will take at least 10 microsecond. Now let me give you another example. Suppose the slew rate of this op-amp was 10 volt per microsecond. So you're going to use an operational amplifier which has a higher slew rate. So in this case, in 1 microsecond, your output will have 10 volt. I mean, it is possible to reach 10 volt. So here you need only 5 volt. So that means your output will take only 0.5 microseconds. So in that case, you see here, your output would have been much better. So if I draw a line here, and this is my 20 microsecond, and this was my 0. You see, in how much microsecond? In 0.5 microsecond. That means it's very small. Immediately your signal would have reached the output. This time delay was only 0.5, which is very small compared to 20 microsecond, and your output will stay like that. And to reach from 5 to 0 also, it will take only 0.5 microsecond, which is again very small. You understand? So when you use a higher slew rate, that means you are going to get a better output. So this is the idea behind slew rate. Now, the concept of slew rate will help us to find out something called as the maximum signal frequency for which you can work your operational amplifier. So what is maximum signal frequency? Because slew rate and maximum signal frequency usually comes together. So maximum frequency, signal frequency of an operational amplifier depends on both the bandwidth and the slew rate of an op-amp. Now let us see how do we calculate the maximum signal frequency of an op-amp. Now you see here, I'm going to take an example of a sine wave. So for a sine wave, I'm going to write V is equal to Vm sine omega t. I think all of you know how to write a signal. You must have studied in your communication system. You might have studied in your AC electrical. If you look at this equation is very much similar to what is given. There I have written V0 is equal to K into sine. What is your omega? I think all of you know omega. Omega is 2 pi f. So I'm going to write 2 pi f t. So this is the same equation. So always remember that K is your Vm, your V0 is actually your V, and this omega is your 2 pi f t. Now I'm going to find out the rate of change of this signal. So I'm going to find out how much is dV0 divided by dt. So K is a constant, or Vm. So let me differentiate the first one so that it is easy for you and something which you already know. So it is equal to Vm into, Vm is a constant. The differential of sine is cos omega t and multiplied by omega. So if I write it for the second equation, it would be K into cos 2 pi ft into t into 2 pi f. So this is your dV0 by dt. Now what I'm going to do is that I want to find out the maximum value of this. That is equal to, the maximum value of this is found out by the maximum value of cos omega t. What is the maximum value of cos omega t? It is 1. So it is equal to K into 1 into 2 pi f. Okay. So the maximum rate of change of the signal is given by 2 pi f k, which is the maximum rate of change. This is what is given here. See here. And the unit of this is given as, it's dV by dt, so it is volt per second. Okay. Now, if you want to prevent distortion of the signal at the output, we saw what is distortion. Distortion is there is a change in the expected output. That means the output will have a change in shape. So to prevent distortion at the output, the condition that we have to follow is that the rate of change of the signal should be always less than the slew rate. So that means, or the slew rate should be always greater than the maximum rate of change of the signal, or 2 pi fk should be less than or equal to slew rate. Understood? So let us take the worst condition. So let us assume 2 pi fk is equal to slew rate. Okay, or 2 pi f is omega, so omega k is equal to slew rate. Now the condition for maximum signal frequencies, that means 2 pi f k should be less than or equal to slew rate. So if I'm going to write it as f maximum, it should be equal to slew rate divided by 2 pi kilo, sorry, not kilo, k is the constant, k hertz. And if I take the 2 pi to the other side, so 2 pi f max is equal to slew rate divided by k. So 2 pi f is omega, so omega should be less than or equal to slew rate divided by k. Now the unit of omega is radians per second. So this is the condition for maximum frequency in a operational amplifier, and you have seen that how does it depend on the slew rate. So slew rate and maximum signal frequency are two parameters which will help us to identify the frequency limitation or the bandwidth limitations of a operational amplifier.